So it's a little bit of conceptual theoretical study. There's a part on measurements and there's a part on CFD biokinetic modeling. I would also like to thank all our partners that helped in this presentation and in this research. So 3 utilities from the Netherlands, Drentse-Overijsselse Delta, Brabantse Delta, and Waterboard de Dommel. And then Explicit from Denmark and Air Liquide. Let's maybe first start why. Why pure oxygen? Because it has a potential of reducing N2O emissions. But next to this, like we already heard also this afternoon in the keynote from Griap, we will have a lot of maybe hydrogen plants in the future. What will they do with the pure oxygen? So there are a lot of co-benefits as well. And then micropollutant removal with the new EU legislation. Ozonation is an interesting technique over there. You will have an off gas with pure oxygen, so this can be reused in the process. A lot is about process intensification in general. Also there, pure oxygen can be an interesting technology to further dive into. So that's a bit the background on why this conceptual study started. So now let's zoom in on really the N2O stuff. What is the effect of pure oxygen on N2O? Let's maybe first start with the measurement part. So in the wastewater treatment plant Hessenpoort in the Netherlands, they already did some preliminary measurements. So water utility Drentse-Overijsselse Delta, together with STOA and the European Union and N2O, did this first research already. So they have their an aeration system with fine bubble aeration actually. So with diffusers at the bottom. And they actually already tried there what is the effect of pure oxygen in general on the performance. So they use the same gas flow in each diffuser, but just used way less diffusers in general because you need less gas flow if you use pure oxygen. The overall observations in this first research was that you could actually 4 to 6 times less gas was needed to actually have the same oxygen transfer efficiency. But regarding N2O, it was difficult to already draw conclusions. So they measured in the liquid phase and gas phase, but in general the emissions were rather low, so difficult to really draw conclusions about that. So that's where we helped them with a conceptual study on to further dive into this research. So maybe first a little bit on N2O emissions to explain how you in the end up with emissions. So it's a 3-step process. First, it actually starts with production. So you have the different pathways that can lead to N2O production. So that's really in kilograms per cubic meter per second, how much is being produced, where in the reactor. All depends on your local concentrations in your reactor. So that's production. And then it ends up in a concentration in the water phase. And then everything is moving in a bioreactor. So your N2O is being transported in your bioreactor. So this is what you can measure with the liquid phase sensors. And then when the air or the pure oxygen is being added, you actually get the stripping effect. So it's going from the liquid phase to the gas phase, and this ends up as emissions. Just important to understand in general this scheme a bit. So let's now go more into the details on the pure oxygen. First, let's start with the physics. What can be the effect of applying pure oxygen? Because you use way less gas to introduce this oxygen, it will have a big effect on the stripping of N2O. Because you have higher concentrations, you will have higher dissolved oxygen concentrations, and you have a faster mass transfer. Because you use less gas flow, you can have less mixing in certain zones. Of course, there is specific equipment that can improve the mixing. There are technology vendors selling this technology. So in the end, that's the physics, but what's then the effect on the biology? Then we can go a little bit more into the details, but in general, the 3 items I just mentioned here, green means it's a positive effect on the N2O emissions, and red, of course, a negative effect. So if we look at stripping, for example, you have less stripping. A very important effect of that is, of course, you have less emissions, but also the N2O stays longer in the liquid phase. And because it stays longer in the liquid phase, you actually also have more consumption of N2O. So this pathway in the denitrification step consumes more N2O because it stays more in the liquid. If you have higher dissolved oxygen concentrations, for example, this, depending on which pathway, has a positive or a negative effect. It can be that you have less production by a pathway, it can be that more production. So if you want to really capture these details, I would say take a picture or look at the presentation afterwards. But yeah, all these things have an effect. The question is, what's in the end the net effect? And that's rather difficult to say. So that's why we use actually the CFD N2O model, so where we combine the physics with the biology, so that in 3D you can see all those concentrations and really understand what is happening in your reactor. So we built a small-scale virtual pilot, a virtual reactor. You can see it here, so it's an anoxic chamber at the left side, where all the incoming flows are there. Then you have an aerobic chamber with all the diffusers at the bottom. So that's a bit how it looks like. And in the next slides, we will always look from the front side. So you will see a vertical cross-section with on the left side this anoxic chamber, on the right side the aerobic chamber. Let's first look at the dissolved oxygen concentrations. On the top, you always see conventional air, at the bottom, pure oxygen. So you see, in general, a little bit of a different behavior of the dissolved oxygen concentrations. And in general, the oxygen transfer efficiency is a bit higher with the pure oxygen. The pure oxygen is only injected in diffusers. With specialized equipment, you can get way higher. So that's dissolved oxygen. If we look at these things, this will have an effect on your N2O concentrations, because this will influence all the pathways. So this different pattern will influence all the pathways. Then let's see stripping. So what is stripping? It's the N2O going from the liquid phase to the gas phase. Yeah. So you see here kilograms N2O per cubic meter per second that are going to the gas phase. Because you use way less gas, you actually, the mass transfer is 5 times lower in general. So you have way less N2O coming into the gas phase. Then you see the pathways here. So here we are talking about production. So how much is being produced by the heterotrophic denitrification? It's in the anoxic zones that this is happening. So kilograms per cubic meter production of N2O per second. You see here in the pure oxygen case, there's a little bit more production with this pathway, but there's also more consumption with this pathway. That's not shown here on this slide, but we also have this figure and it's more consumption there. Other pathways, AOB denitrification, you actually see here this swirl a bit. But in general, the low DO concentrations are lower you see less lower DO concentrations. And this is why the AOB denitrification pathway, you have actually less production here. So we have this for all the pathways. Here is the hydroxylamine pathway. There's more production with this pathway. And in the end, we come to an overall effect. We have these pathways. Step 1, the production. We have the liquid phase concentrations. And then we have the mass transfer and in the end, the emissions. So based on that, we can actually calculate the overall emissions. And if we make the comparison here, so you have the emission factors based on the ammonia removed on the left side and based on the incoming ammonia on the right side. And actually we see that if you use diffusers with pure oxygen, you can lower your emission factor in the gas phase by 5 times as compared to the diffusers with conventional aeration. So in general, the conclusions here are that the pure oxygen really has the potential to reduce the N2O emissions. Why? Because the stripping, you reduce the stripping a lot. You have certain zones where there's a higher production. You maybe measure a little bit more sometimes with a liquid phase sensor, but there's also more consumption. And in the end, this reduced stripping promotes even further this consumption. Next to this, other possible advantages are you gain some additional denitrification volume, or you can intensify your process even more. Some risks, if you use this with diffusers, you need to make sure that there is enough mixing in your system to prevent sludge settling, but also there specialized equipment to have enough mixing and increase this oxygen transfer even further. Now, what are the next steps? So this was purely a conceptual study with a small-scale virtual reactor. Now the next step is going to the full scale. And next year there will be a demo with this, there will be an H2 hydrogen production plant be built in the wastewater treatment plant of Hesselpoort. And the pure oxygen will then be used in this reactor. So that will start next year. So we will have way more data there. And we will also apply our CFD N2O model to this full-scale plant to analyze the effects. And we will focus there on N2O, of course, but also on effluent quality. And then I hope we can communicate about the results within a year or a year and a half. Let's see. Thank you for listening.